is automatically available to do things in this picture language. The technical term I want to say is not only is this language implemented in Lisp, which obviously is, but the language is nicely embedded in Lisp. And what I mean is, by embedding the language in this way, all the power of Lisp is automatically available as an extension to whatever you want to do. Now, what do I mean by that? Example. See, suppose I want to make a thing that takes 4 pictures, right? A, B, C, and D, and makes a configuration that looks like this. You might call that 4 pictures or something. 4-picked configuration. How do I do that? Well, I can obviously do that. I just write a procedure that takes B above D and A above C and puts those things beside each other. So I automatically have Lisp's ability to do procedure composition. And I didn't have to make that specifically in the picture language. It's automatic from the fact that the means of combination are themselves procedures. Or suppose I wanted to do something a little bit more complicated. I wanted to put in a parameter so that for each of these I could independently specify a rotation by 90 degrees. That's just putting a parameter in the procedure. It's automatically there. Right? It automatically comes from the embedding. Or, even more. Suppose I wanted to, use recursion. Let's look at a recursive means of combination on pictures. I could say define. Let's see if you can figure out what this one is. Suppose I say define what it means to right push a picture. Right push a picture and some integer n and some scale factor a. I'll define this to say if n equals 0, then the answer is the picture. Otherwise, I'm going to put, name change, P. Otherwise, I'm going to take P and put it beside the result of recursively right pushing P with n minus 1 and a, and use a scale factor of a. Okay, so if n0, it's p. Otherwise, I put p with the scale factor of a. I'm sorry, I didn't align this right. Recursively beside the result of right pushing p n minus 1 times with a scale factor of a. There's a recursive means of combination. What does that look like? Well, here's what it looks like. There's George. Right, there's George right pushed against himself twice with a scale factor of 0.75. Okay, where'd that come from? How did I get all this fancy recursion? The answer is just automatic. Absolutely automatic. Since these are procedures, the embedding says, well, sure, I can define recursive procedures. I didn't have to arrange that. And of course, we can do more complicated things. The same sort, I could make something that does an up push, right? That sort of goes like this, by recursively putting something above. Or I could make something that sort of was this scheme. I might start out with a picture and then sort of recursively both push it beside and above. And that might put something there. And then up here I put the same recursive thing. And I might end up with something like this. Right, so there's a procedure that's a little bit more complicated than right push, but not much. I just do an above and a beside rather than just a beside. Okay. Now if I take that and apply that with the idea of putting 4 pictures together, which I can surely do, and I go and I apply that to Q, which we defined before, right, what I end up with is this thing, which is sort of the square limit of Q done twice. Right, and then we can compare that with Escher's square limit. And you see it's sort of the same idea. Escher's is, of course, much, much prettier. If we go back and look at George, right, if we go look at George here, see, I started with a fairly arbitrary design, this picture of George, and did things with it. Right, whereas if we go look in the Escher picture, right, the Escher picture is not an arbitrary design. It's this very, very clever thing, so that when you take this fish body and rotate it and shrink it down, it bleeds into the next one really nicely. And of course, with George, I didn't really do anything like that. So if we look at George, right, there's a little bit of matchup, but not very nice, and it's pretty arbitrary. One very nice project, by the way, would be to write a procedure that could take some basic figure, like this George thing, and start moving the ends of the lines around, so you got a really nice one when you went and did that square limit process. That'd be a really nice thing to think about. Well, so we can combine things, we can have recursive procedures, we can do all kinds of things, and that's all automatic. Right? The important point, the difference between merely implementing something in a language and embedding something in the language, so that you don't lose the original power of the language, and what Lisp is great at. See, Lisp is a lousy language for doing any particular problem. What it's good for is figuring out the right language that you want and embedding that in Lisp. That's the real power of this approach to design. Of course, we can go further. See, you saw the other thing that we can do in Lisp is capture general methods of doing things as higher order procedures. And you probably, just from me drawing it, got the idea that right push and the analogous thing where you push something up and up and up and up, and this corner push thing are all generalizations of a common kind of idea. So just to illustrate and give you practice in looking at a fairly convoluted use of higher order procedures, let me show you the general idea of pushing some means of combination to recursively repeat it. Right, so here's a good one to puzzle out. We'll define what it means to push using a means of combination. And comb is going to be something like beside or above. Well, what's that going to be? That's going to be a procedure. Remember what beside actually was. Right? It took a picture. Took two pictures and a scale factor. Using that, I produced something that took a level number and a picture and a scale factor that I called right push. So this is going to be something that takes a picture, a level number, and a scale factor. And it's going to say, I'm going to do some repeated operation. I'm going to repeatedly apply the procedure which takes a picture and applies the means of combination to the picture and the original picture and the one I took in here and the scale factor. And I do the thing which repeats this procedure n times. And I apply that whole thing to my original picture. Repeated here, in case you haven't seen it, is another higher order procedure that takes a procedure and a number and returns for you another procedure that applies this procedure n times. And I think some of you have already written repeated as an exercise, but if you haven't, it's a very good exercise in thinking about higher order procedures. But in any case, the result of this repeated is what I apply to picture. And having done that, that's going to capture that is the thing, the way I got from the idea of beside to the idea of right push. So having done that, I could say, define right push to be push of beside. Or if I said define up push to be push of above, I'd get the analogous thing, or define corner push to be push of some appropriate thing that did both of beside and above, or I could push anything. Anyway, this is if you're having trouble with lambdas, this is an excellent exercise in figuring out what this means. Okay. Okay, well, there's a lot to learn from this example. The main point I've been dwelling on is the notion of nicely embedding a language inside another language, right? So that all the power of this language like Lisp, of the surrounding language, is still accessible to you and appears as a natural extension of the language that you built. That's one thing that this example shows very well. Okay. Another thing is, if you go back and think about that, what's procedures and what's data? You know, by the time we get up to here, my God, what's going on? I mean, this is some procedure, and it takes a picture and an argument. And what's a picture? Well, a picture itself, as you remember, was a procedure, and that took a rectangle, and a rectangle is some abstraction. And I hope now that by now you're completely lost as the question of what in the system is procedure and what's data. You see, there isn't any difference. There really isn't. And you might think of a picture sometimes as a procedure and sometimes as data, but that's just sort of, you know, making you feel comfortable. It's really both in some sense, or neither in some sense. Okay. There's a more general point about the structure of this system, the structure of a system as creating a language, viewing the engineering design process as one of creating a language, or rather one of creating a sort of sequence of layers of language. You see, there's this methodology, or maybe I should say mythology, that's sort of charitably called software, quote, engineering, right? And what does it say? It says, well, you go and you figure out your task and you figure out exactly what you want to do. And then once you figure out exactly what you want to do, you find out that it breaks out into 3 subtasks. So you go and you start working on, and you work on this subtask, and you figure out exactly what that is, and you find out that that breaks down into 3 subtasks, and you specify them completely, and you go and you work on those 2, and you work on this sub one, and you specify that exactly, and then finally when you're done, you come back way up here, and you work on your second subtask and specify that out and work it out, and then you end up at the end with this beautiful edifice, right? You end up with a marvelous tree where you've broken your task into subtasks, and broken each of these into subtasks, and broken those into subtasks, right? And each of these nodes is exactly and precisely defined to do the wonderful, beautiful task to make it fit into the whole edifice, right? That's this mythology. See, only a computer scientist could possibly believe that you build a complex system like that, right? Contrast that with this Henderson example. It didn't work like that. What happened was that there was a sequence of layers of language. What happened? There was a layer of a thing that allowed us to build primitive pictures. There's primitive pictures. And that was a language. I didn't say much about it. We talked about how to construct George, but that was a language where you talked about vectors and line segments and points and where they sat in the unit square. And then on top of that, right, on top of that, so this is the language of primitive pictures, right, talking about line segments and particular pictures in the unit square. On top of that was a whole language. There was a language of geometric combinators, right? A language of geometric positions, which talks about things like above and beside and right push and rotate. And those things sort of happen with reference to the things that are talked about in this language. And then if we like, we saw that above that, there was sort of a language of schemes of combination. For example, push, which talked about repeatedly doing something over with a scale factor. And the things that were being discussed in that language were sort of the things that happened down here. So what you have is, at each level, the objects that are being talked about are the things that were erected at the previous level. What's the difference between this thing and this thing? The answer is that over here in the tree, each node, and in fact each decomposition down here, is being designed to do a specific task. Whereas in the other scheme, what you have is a full range of linguistic power at each level. See, what's happening there at any level is it's not being set up to do a particular task. It's being set up to talk about a whole range of things. The consequence of that for design is that something that's designed in that method is likely to be more robust. Where by robust, I mean that if you go and make some change in your description, it's more likely to be captured by a change, by a corresponding change in the way that that the language is implemented at the next level up, right? Because you've made these levels full. So you're not talking about a particular thing like beside. You've given yourself a whole vocabulary to express things of that sort. So if you go and change your specifications a little bit, it's more likely that your methodology will be able to adapt to capture that change. Whereas a design like this is not going to be robust, because if I go and change something here, that might affect the entire way that I decomposed everything down, further down the tree. Right? It's a very big difference in outlook in decomposition, levels of language, rather than sort of a strict hierarchy. Not only that, but when you have levels of language, you're giving yourself different vocabularies for talking about the design at different levels. So if we go back and look at George one last time, if I wanted to change this picture George, see, suddenly I have a whole different ways of describing the change. Like, for example, I may want to go to the basic primitive design and move the endpoint of some vector. That's a change that I would discuss at the lowest level. I would say the endpoint's somewhere else. Or I might come up and say, well, the next thing I wanted to do, this little replicated element, I might want to do by something else. I might want to put a scale factor in that beside. That's a change that I would discuss at the next level of design, the level of combinators. Or I might want to say, I might want to change the basic way that I took this pattern and made some recursive decomposition, maybe not bleeding out toward the corners or something else. That would be a change that I would discuss at the highest level. And because I've structured the system this way, I have all these vocabularies for talking about change in different ways and a lot of flexibility to decide which one's appropriate. Okay, well, that's sort of a big point about the difference in software methodology that comes out from Lisp. And it all comes, again, out of the notion that really the design process is not so much implementing programs as implementing languages. And that's really the power of Lisp. Okay, thank you. Let's take a break.